Hey everybody, in this video we're going to talk about solving differential equations even if they aren't exact. So in the last video we talked about verifying whether a differential equation was exact and then finding the solution. Here we're going to take differential equations that may not be exact to begin with, but we're going to transform them so that they become exact, and then we'll be able to solve them. Okay, so let's go down and take a look at an example we actually had from the last video, and we showed that this was not exact. And we did that by looking at the y derivative of this term, which is 1, and the x derivative of this term, which is 2. Since those aren't equal, the differential equation is not exact. So we didn't solve this, right? We just said it's not exact, there's nothing more we can do. Turns out there is something else we can do, and we're going to explore that in this video. So what we're going to do is we're going to try multiplying through this entire equation by a function of x. And I'm going to call it mu of x, the Greek letter mu. So let's multiply through by mu of x and see what happens. Okay, so we have this differential equation. So what we have here is we have a differential equation of the form m dx plus n dy equals 0. Now to test this for exactness, as we talked about in the last video, we need to check to see whether my, the y derivative of x, is equal to nx, the x derivative of n. If that's true, then the differential equation is exact. Okay, so let's check this. Here's our m, so we're going to take the y derivative of m. Okay, so let's see what we get. Well, that's easy because this is just a linear term here. So the y derivative of m is just mu of x. Okay? Now, what about the x derivative of n? I have to take the x derivative of this. Well, that's 2 mu of x plus 2x mu prime of x. Okay, so now we have a differential equation. If we can find a mu so that this differential equation is solved, right, then we will have transformed this into an exact differential equation because this will be satisfied. All right, so now our goal is to solve this differential equation. Well, you can do that by this is a separable differential equation. So here, what I'm going to ask you to do is pause the video, solve this for mu, and then we'll come back and compare our answers. Okay? So 3, 2, 1. All right, welcome back. Let's check our work here. What you'll end up with is mu prime over mu is equal to negative 1 over 2x. Right? Yeah. This is what you should have gotten. Okay, so when you proceed to solve this, what happens? Well, what do we get here? We get, I'm going to skip to the chase here. I trust you can show the work in between. You should get to mu equals 1 over root x. Okay? Go back, watch our other videos on solving this type of differential equation to see the steps here. Okay, but we've found what mu has to be. All right, that's the mu that if we were to put it up here would make this an exact differential equation. So let's go ahead and multiply through by this in our original differential equation. So in place of mu, I'm going to put 1 over root x here. So in other words, I'm going to have y plus 1 over root x, 2x over root x. Well, that's just 2 root x dy equals 0. So by multiplying through by this function, we've transformed our differential equation into this one. And we know that this one is exact. So now we can find the solution, right? So how would we do that? Well, we know that this has to be the x derivative of some function. So our function must be the integral with respect to x. And at the same time, this has to be the y derivative of that function. So f has to be the integral of this with respect to y. Now I'm going to do a further trick here, just to simplify things. There's a little bit of a trick that I didn't talk about in the last video to make things easier. What we did last time was we computed both of these, and then we matched them up. What I'm going to do in this one is just compute the bottom one, and I'm going to get at the top one by another means, okay? So it doesn't matter. You could do it the other way. I just want to point this out. This is the reason I'm doing this is because looks like an easier integral to do than this one, all right? Because here x is constant with respect to y, so I know the answer is just 2 root x y plus some function, we called it h I think before, some function of x. Now, when I take the derivative, since this is f, and f is the antiderivative of this with respect to x, that means the derivative of this with respect to x must equal this. Okay? So let's just check that. All right? If I compute fx here, what do I get? I get 1 over root x times y plus h prime of x. And that should equal this, right? We can use this to find what h is going to be. Okay, so if I just subtract 1 over root xy from both sides, I see that h prime of x is equal to 1 over root x. So therefore, h of x must equal 2 root x. That's a different method than we used last time, but it works out the same way. Okay, so we found it. We found what f is. All right, f is 2 root xy plus 2 root x. Or in other words, it's 2 root x times y plus 1. Okay, now, how do we write our final answer? Well, once we found f, we know that our final answer is of the form f of xy equals a constant. In this case, this is our function, so there we have it. That's the answer to our differential equation. That's the solution. Okay, so even though the original differential equation was not exact, we were able to multiply by something to make it exact. Now this thing that we multiplied by, that is called an integrating factor. See if I'll scoot myself out of the way here. That's an integrating factor. And that's the idea, is finding these integrating factors so that we can do this. So you're always going to check to see if it's exact. If it's exact, you don't have to do this, right? But if it's not exact, look for an integrating factor. Now, here what we did is we just guessed that it might be some function of x, and it happened to work. So if you look in your book, they give you a little bit more insight on how to make this guess, all right? So let's go take a look at your book here. If we look at theorem 2.6.1, they tell you exactly what's going on. So the integrating factor, so here's our differential equation, right? What we're going to do to find mu is we're going to compute my minus nx and divide by n. Right? Now, if that is independent of y, then mu is going to be e to the antiderivative of that. That's how we get mu. Now, if it's independent of x instead, then it's going to be a function of y, and mu will be a function of y instead of a function of x, and mu will be e to the antiderivative of that. All right, let's go look back at our problem and see how that applies to what we did. All right, so let's see. We had our differential equation up here. Okay, so here's what they're calling m, and here's what they're calling n. So what we need to do in this, let me get another sheet of paper here. we need to compute, they asked us to look at my minus nx over n. Okay, so let's see what we get here. Well, my, the derivative of this with respect to y, is just 1. Nx, this is 2. Divide by n, 2x. This is just negative 1 over 2x. That's independent of y. So what did they say next? If that's independent of y, then let p be this thing, the thing we just computed, right? And then mu is the e to the plus or minus e to the antiderivative of that. Okay? So what they're saying is they're saying for your mu, you should take this, e to the antiderivative. It's going to be plus or minus e to the antiderivative of that guy. Well, guess what happens when you simplify this? Sure enough, you get exactly what we found. You get exactly 1 over root x, which is exactly the integrating factor that we found. Okay, so we did it by a kind of guess and check approach. We just said, hey, maybe there's a mu, let's multiply through, let's see what happens. And we solved for mu. What the book is telling you is that, well, hey, all you really got to do is just check this quantity. If it's independent of y, then here's your mu. And if it's independent of x, they tell you how to do it that way as well. Okay, so let's go ahead and look at another example. Let's take a look at this one. Okay, I'm in the way. Okay, so here's our differential equation. And so let's just go right to the book and see what it suggests that we do here. It says to check this thing, right? And see if it's independent of y. And if that doesn't work, we're going to check this guy and see if it's independent of x. Whichever one works out, we're going to let mu be e to the antiderivative of that guy. Okay? So the first one it said to check was my minus nx over n, right? So let's compute those things. Let's compute my and nx. Okay, so my is the derivative of this with respect to y, so that's 6xy squared, and nx is the derivative of this stuff with respect to x. Okay, well that's going to be this guy. Okay, so let's check it out. What is my minus nx over n? Okay, well let's see, that's this minus this. What's n? N is this whole thing. Okay, let me just put a scribble in there where we understand that's this. Okay. Now the question is this independent of y? Sorry. Well, okay, these things cancel off right here, but then I'm going to have this guy divided by all this junk. Well, that's got x's and y's in it, so that's not independent of y. So, sorry, didn't work out. Okay, but then the book said, okay, well then check this and see if it's independent of x. Okay, so let's do that. It's nx minus my over m. Okay, and see if this is independent of x. Right? So let's see what we get here. Now notice that nx minus my is just the negative of my minus nx. Right? So I'll just take the negative of this stuff. Well, look, the 6xy squared canceled, and so I just end up with 2xy cubed. And I'm dividing by m. What was m? Well, m was this guy, 2xy cubed, right? Okay, well, this is just 1. Is that independent of x? Absolutely. So there we go. That's what we have to use. So what we're saying is that mu, the book says to let mu be plus or minus e to the antiderivative of that, dy, right? If it's independent, if this thing is independent of x, then you treat mu as a function of y. All right, so what is that? That's just plus or minus e to the y. Okay, the plus or minus doesn't really matter here. Why don't we just take the positive e to the y? Both work as integrating factors. That's what that's saying. You could have plus or minus, but since either one works, let mu be either one. So we'll just take the positive one. Okay, so what we're going to do is we're going to multiply our differential equation through by e to the y. Okay, so let's see what happens when we do that. All right, so we're going to have 2xy cubed e to the y. Okay, we get this. And now let's see what we can do with this. So if you notice, we need to find the function f by anti-differentiating this with respect to x and anti-differentiating this with respect to y. All right, I don't know about you, but I'd rather do this one first. Okay, so f is going to be the antiderivative of this guy. All right, and when we do that, what do we get? Just this. Plus some function of y. Now, like I did before in the previous problem, I'm not going to go through and try to find the antiderivative of this thing. That's actually going to be a pain in the butt. Instead, I'm going to use the fact that I know that if I take the y derivative of this, I'm supposed to get to this. So let's just compute the y derivative of this, set it equal to that, and solve. All right, so let's take fy. What do I get here? I get this thing. Now this is supposed to be the same as this. So I can just match up terms. Notice that this term is the same as that. This term is the same as that. And this will just be this, right? Remember, I'm distributing the e to the y through. So that means that g prime of y has to equal e to the y. So what we'll do is we'll just take g of y to be e to the y. And remember what we said before, adding a constant doesn't really matter here because of the next step. We're going to be setting it equal to a constant, so that'll be taken care of. Okay, so that's, well, we got it, right? This is circling the wrong thing there. This is our function, right? Where this is in place of g, all right? So our answer is and perhaps an easier way to, a nicer way to write it would be I like that. Okay, there we go. Okay, so I have one more example for you that's a little bit different. We're going to have to do something a little bit special here. So let's go to this one. All right, so for this differential equation, we're going to try the same thing, right? We're going to look at these quantities. We're going to look at my minus nx over n, and we're going to look at nx minus my over m, and see if either of these is independent of the corresponding variable, right? So let's see, my, that's this thing, derivative with respect to y, minus the derivative of this with respect to x, divided by n, 1 over xy. Now, we need this to be independent of y, right? Is it going to be? Well, I can tell it's not going to work out because of this y squared over here. There's no way that this stuff is going to cancel out a y squared. So that's not going to work. Oh well. So what do? We check the next one. Okay, maybe we'll have hope here. And remember, this numerator is exactly the negative of that numerator. So I know that this is just going to be this thing. And what's m? M is 2 over y. and I have the same problem. There's no way I can, oh, I need this to be independent of x, right? There's no way I can clear out this x. So again, bummer, right? Not working. So neither one worked. So I can't get my mu from that theorem, okay? Well, here's another idea to try. Okay, so remember how we got to this. We got to this by multiplying through by a function of x or multiplying through by a function of y. Well, what if it's something a little bit more general than that? What if it's a function of x times a function of y? Let's try that, okay? So let's go ahead and multiply through by a function of x times a function of y. So I'll do p of x, q of y. And let's see what we get from this. Okay, so well, how did we go through it in the very first example? Well, we need the derivative to check for exactness. We need the derivative of this with respect to y to be the derivative of this with respect to x. So let's compute those derivatives. Okay, so I'm just going to stop writing the x's and y's here. Just write p and q, understanding what they're functions of. Okay, so differentiate with respect to y. Okay, this will be a negative 2 over y squared. And then differentiate, oh, and that's supposed to equal this stuff with respect to the derivative with respect to x. These need to be equal. Okay, so what do we do now? Well, I think a good thing to do would be to divide everything by PQ. Divide everything through by PQ. What do we get? Oh, I can just do this, right? Okay. Why don't we I'm going to let lowercase q be this thing, and I'm going to let lowercase p be this thing. All right, so this is lowercase q, this is lowercase p. Moreover, what I'm going to do is I'm going to multiply through to clear out all the denominators. So I'm going to multiply through by x squared y squared. Okay, let's see what we get. So we get lowercase q, we get times 2 x squared y, because one of the y's cancels. Here the y squared cancels. Here I'm going to have p x y, and here the x squared cancels, leaving us with just a y. So this is what I get. All right, what can we do with this? Well, let's see. I see. Let's collect the p and the q's on the left, right? So I need what's on the left to equal what's on the right. All right. So that means I need px to be 1 so that I get the minus y, and I need qy to be 1. All right. Do you see that? If px equals 1 and qy equals 1, then these will be the same. So that tells us what p and q are. P has to be 1 over x, and q has to equal 1 over y. And that is totally copacetic, right? Because we were saying that q was a function of y, right? And little q is just q prime over u, so it's a function of y. So it's totally legitimate to write it as a function of y like this, right? And similarly for x, right? So unwinding all this, remember what we want to do is we want to find p times q. That's going to be our integrating factor, right? Well, how do I find that? Well, I know how they're related, right? P is just p prime, capital P prime over capital P, right? So I know that capital P prime over P is 1 over x, and I know that capital Q prime over Q is 1 over y. Okay, so all we have to do is solve these differential equations. So we get a very simple solution here. We get P equals X and Q equals Y. That may not be obvious, but just go through the steps of solving differential equations to get to these answers, and you'll see this is exactly what we get. And so our integrating factor in this case, mu, is going to be xy. Okay, so let's go to the differential equation and apply this. Was this? We're going to multiply through by the integrating factor xy. And let's see what we get. We get 2x dx plus dy equals 0. And so now I need to find my f. I think the easiest way to get it would be to anti-differentiate this. So f is the antiderivative of dy. So that means so f is y plus some function of x. And if I differentiate this with respect to x, I should get this. Right? But when I differentiate this with respect to x, I get g prime of x. So that tells me that g of x must equal x squared. And again, I don't care about this constant. And so that's my function, right? My function is y plus x squared. And we set it equal to a constant, and that's our solution. Okay, so 3 examples there of using integrating factors to solve these differential equations. They aren't exact to begin with, but by multiplying through by the integrating factor, they become exact. All right, so that's it for exact equations, and I'll see you in the next section.